In this slide, we will talk about the magnitude dependence of errors. And for iterative processes, especially when we use the numerical methods, we need to test whether two numbers are equal in two cases. Because we want to have an error value, for example, smaller than a pre-specified value like epsilon s that we did in the previous examples. We can use it as a stopping mechanism or as a convergence criteria. So there are two ways. In the previous examples, for example, for the parachutist example or the exponential prediction with the Maclaurin series, we used the stopping mechanism. We used to have our epsilon a, for example, should be smaller than epsilon s. And when this is smaller than epsilon s, we stopped. So that's the stopping mechanism. Or we can say it should be a convergence criteria. Convergence criteria means the difference between two errors should be smaller than something. Like, let's say EA I minus EA I plus 1 should be smaller than a value. So if the difference is smaller than a value, that means the result, the error result, will converge. Then that means we have a convergence criteria. So two ways of considering the equality of two numbers. But having equality, actually we say this should be equal, but having equality is too strict because of the large number of digits, we will not be able to have the exact same number for two numbers. So that means that's too strict. That's why we need to relax, and for the relaxation we use this smaller than or greater than symbol, basically less than, and acceptably small tolerance. That's why we use these. We basically relax the equality here. Also, the magnitudes of the values can be so different, and the difference of the magnitudes is important because in that case we need to normalize the results. We already mentioned this before, and by normalizing we need to compare the results so that we can have fair understanding of the error or the value. And the machine epsilon that we mentioned earlier for the round of error, for example, we use that as a stopping criteria or a comparison criteria in an example. And it can be used for formulation of stopping or convergence criteria, basically as a threshold value epsilon s, for example. This ensures that the programs are portable because machine epsilon is dependent on the computer or the type of the bit number, 8-bit, 7-bit, etc. That's why if we have this as a stopping criteria, the machine epsilon, we can use the same program in a different computer. That means it will not be dependent on one computer on which they are implemented. We can simply use it in another computer as well. With this stopping criteria, change of this stopping criteria in another computer will be fair enough to be able to evaluate the results. So the pseudocode to automatically determine the machine epsilon of a binary computer is given as shown here. So to be able to decide that, we will have a do and do algorithm, and in this epsilon plus 1 should be smaller than 1, and if it is correct, then it finishes, and epsilon is defined as 2 times epsilon. If not, epsilon is divided by 2, and it continues until this condition satisfied. So this can be used for different computers as well. And in this slide, we will talk about the extended precision. We already mentioned about long format long in MATLAB, for example, in an example before. This is actually used to extend the precision of the computer. Usually, the current computers use IEEE format, which allows 24 bits to be used for the mantissa. So there is the mantissa part, 24 bits. Also, there is exponent part and sign part. For the mantissa, usually 24 bits are used by default, let's say. And this translates into 7 significant base, 10 digits of precision with a range of about 10 to the power minus 38 to 10 to the power 39. And this is called also single precision. Especially in MATLAB, it is called single precision. But we can still increase the number of bits in the computer to show, but this will require more memory and more operations. But that's okay. If we need extended precision, we can increase the precision of the numbers, demonstration of the numbers. Sometimes because the round of error can be very critical. In that case, we use double precision instead of single precision, and we increase the number of bits. For example, the floating numbers, point numbers, or the mantissa size is doubled in this case, and from 7 to 15 or 16 decimal digits of precision can be used, and the range of approximately 10 to the power minus 308 and to 10 to the power 308 range. As you can see, the range is 10 times almost in the power, let's say. And in many cases, the use of double precision quantities can greatly mitigate the effect of round of errors, but there is a trade-off because it will require more memory and more execution time. So if you are using some analysis, iterative analysis, if you use this kind of large storage, it will require too much memory, and you need really too much RAM or hard drive, and also execution time. You need a powerful processor. I mean, the current computers are okay with this kind of double precision, but still, in some cases, there is no need for this, and we can just continue with single precision. If it doesn't work well with single precision, then we can consider about the double precision as a last resort maybe. With all of this information, we ended chapter 3, and you can read chapter 3 in your book if you want to learn more about this kind of significant digits and the round of errors. And thank you very much for listening. See you in another class.